Okay, welcome back, students. We'll start lecture now. I want to say nice job to those of you that peppered up the discussions area over the weekend concerning problems 4 and 5. And there was quite a lot of posting back and forth. And I think there were 2 threads where people were talking, and which is all right. Just so you know, I noticed in the thread, which I think is biggest, the title was not very specific. It just said homework 2. So remember, when you post a homework-related question, make the title pretty explicit. So homework title, what's the formula for problem 4, for instance? And then make sure you make it threaded replies and also liking, and then that'll work good. Another thing I noticed, and I'll just pass this on to you, for you, and hopefully it'll make your studying a little more efficient. At the top of the thread, within a first 10 replies, there was somebody typed in the exact formula for the drop time based on the drop distance d. It had a big square root in it. And I noticed that some of the people that posted after that, like at level 20, didn't realize that. You know, they said, I can't get this formula, and the formula was right there. And so what I suggest to you, if you are going in there, and it's a good thing to do to get tips, definitely look at all the postings in there. Otherwise, you're going to end up, replete. And so matter of fact, I replied to somebody, and I said, here's the formula. And, and I actually wrote down both formulas, 1/2 GT squared and then the square root version, the inside out version of it. But, just try to, as I always say, and I say this on exams too, always read carefully. Homework, exams, and I guess in discussions too, especially if there's a lot of posted. I think there were like 40 last time I checked. So, which is great, because discussions can be like a virtual study partner for you. And I think that's really good. Okay, SI today at 3 o'clock. Office hours tomorrow, 11 o'clock a.m. to 1 p.m. in the Physical Sciences building. Last time, let's talk about the distance polygons that we looked at. We'll just review. Here's a velocity graph over time for an object that's cooking along at 2 meters per second. So this is constant velocity. And the graph is just that straight line from the v-axis at a level 2.0 meters per second out parallel to the time axis for a total of 4 seconds. And it was just an example. Then we said, okay, draw in the polygon for which that graph is the very top, and then the t-axis, the time axis, is the bottom, and then the sides are parallel to the v-axis, the velocity axis. You get a rectangle in this case, and then interpret the base times height area of that rectangle as the distance traveled, for which this is the normal formula. So one of the things that I want you to try to connect in your brain is this picture of the velocity graph and the idea of a distance rectangle with this formula d equals vt, or d equals v times delta t. All right. Now, another thing that we took a look at last time was the distance triangle, and we worked it out for the free fall case, and we're going to do a generic case here in just a second. In free fall, we dropped something from the top of the UCF library from a state of 0 meters per second here, where the two axes cross, and then it continually acquired equal increments of downward speed for every second of free fall, giving you a slanted velocity graph. But if you then shade in the polygon, in this case a triangle, you can interpret the area as the distance traveled, and we figured out the formula for that. You know, any old triangle, the formula is 1/2 base times height. For this particular triangle, that works out to 1/2 g t squared, or 1/2 g delta t squared if you want to be technical about it, for this particular picture. All right? And you had some basic calculations to do on that for homework. Now, we're going to do some iClicker questions, so get your clickers ready. And we're going to do some multiple choice, and we're going to do a calculation problem today. And so you're going to enter in a number and then hit the send key. All right? And it works a little bit differently, but have your clickers handy. Before we get to those clicker questions, let's take a look at the generic acceleration situation. All right, so the velocity graph for something like a car accelerating for 0 at this rate, here's the 0 at the start, at the intersection of the velocity axis and the time axis, and then it continually acquires equal increments of forward speed, if it's a car, for every second of acceleration. All right, so it's not just free fall. Free fall is where we started, but in general, accelerations are like this. And hey, you guys, this is idealized. A real car is not going to have perfectly smooth, steady acceleration like this. You know, because the way engines work, they don't always develop the same horsepower at all RPMs and stuff like that for various reasons. But you know, a lot of times you'll have at least a few seconds of smooth acceleration like this. Now the triangle 1/2 BH, 1/2 base times height for this one is 1/2 AT squared. And remember, the letter G is the symbol that is customarily used around the world to denote the free fall acceleration at the surface of the Earth. And for everywhere from the top of Mount Everest to the bottom of the deep blue sea, all the way down in the Mariana Trench in the Western Pacific, G is about 9.8 meters per second squared. So for every second of free fall, wherever humans are anyways, pretty much, on planet Earth, the free fall, you know, if you can catch a dollar bill in this classroom, you can catch a dollar bill pretty much anywhere that humans can go on our planet, because it's always 9.8 meters per second squared of free fall. All right. Now, for a generic acceleration, whatever it happens to be, this is the distance triangle that you're looking at, and there's the distance formula for that. Now, I would like to try some easy calculations and then a little tougher one with the iClicker. So let's try this particular question. Oh, by the way, I haven't started the question yet. I put up a bonus point last night. I don't know, it must have been about 8 o'clock for people that had registered before 8 o'clock last night. If you're still not registered, and I know some of you have been really trying, and I have no idea what's wrong, but we're going to have to, if you can, if you can come to office hours, we'll try to do it together. Matter of fact, you know what I'm going to do? Tomorrow, I'm going to have my office hours in my regular office, room 156. And I'm going to have online office hours. So if you're a person that hasn't gotten your clicker successfully registered, then either come to my office in person or come to the online office hours, and I'll post a link to it tonight in web courses, and we'll try to thrash out your clicker issue. It shouldn't be this hard. It usually isn't, but it's been a pain in the you-know-what this year. I don't know. It's driving me bananas. Anyways, let's try a clicker question. Okay. What's the acceleration for this object? Okay, now this is multiple choice. If you haven't used your clicker before, we're on frequency AA. So hold the power button down, and then it'll start flashing the square in the upper left of the display. And then just type in the letters AA, and then you'll get the Go Nitro and the and the Ready button. All right, so you can go ahead and start voting for this. All right, so there's my velocity graph. I'm just recycling the last page. Total delta V is 3 meters per second. Delta T, all right. And when you guys are working in class like this, in lecture, yeah, definitely, if you get stumped, ask your neighbor. If you get it, if you think you know what you're doing, and your neighbor doesn't, give them a little bit of tips. In other words, you can talk. Yeah. I explained that. They're the same formula. It's just that in free fall, you use the symbol G for the acceleration, that's all. Yeah. It's the same formula, just that it's just like using somebody's nickname. If you're doing free fall, its acceleration is nicknamed G. But whatever you do with G, 9.8 meters per second, that's what you do for any other acceleration. I mean, calculation-wise. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Woo, doggies. We got 220 students voting. Nice. Oh, who went to the game on Saturday? You know what? Do not ever go to the north end zone in section 220. I was sitting up, it was faculty appreciation day, so they appreciate us so much they give us these seats way up in the north end zone, almost at the top. And so I got some cheap seats, and I took my son and his buddy to that, and oh my goodness, I thought my brain was going to explode. Those speakers are so loud over there. I don't know if you guys are sitting over I don't think you have the speakers over in the student section that we do. And man, it was just like, I was getting a headache. I mean, every time that guy said, first down, good enough for another UCF first down, and then he always said, Knights, like that. And oh my God, he said it about 9 million times, and I was going insane. All right, so let's see. Did you guys vote here? All right, let me stop this. Knights. Uh-oh. We have a spread of answers. Yeah, C is the correct one. And hey, you guys remember, meters per second is good to express the unit of measurement for an acceleration, but so is meters per second squared. Now, negative 0.6, that's no good because that's negatory. It's not falling. This is a positive. And let's see. I guess that's the common mistake on that. And here's the calculation. So if you got tripped up on that one, here it is, delta V over delta T. Delta V is the height of the distance triangle. And delta T is the width. All right? So the acceleration, you know what the acceleration is. Height over width, rise over run. What do you call that? Remember that from high school geometry class, rise over run? Slope. All right, so it's basically the slope of the velocity graph. All right, next question, a little tougher. How far does it travel in the first 5 seconds of acceleration? "30 seconds. Ooh, people are starting to blaze in now. This one's kind of cinchy if you remember your basic concepts. 15 seconds. 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Dude. 221 students blazing. Uh-oh. We got some splaining to do. We got a little bit of a spread in the data. All right, now, that's all right. Remember, you're answering. That's where you get your pointage. By the way, today's the first day of official clicking. You're now working on the participation part of your, what do you call it? Your semester grade. And by the way, if you're not registered and you have your clicker, you can still click. I'll record it, and when you do get registered, I'll be able to summarize your pointage. So you're not SOL. But as far as getting the bonus points, you're kind of SOL. But for regular pointage and stuff, so get it all registered as fast as you can. All right, we got some splaining to do here. So let's take a look. This is the answer, 7.5 meters. I saw a guy over here go, yeah. And let's just look at it. All right, now here's the triangle formula, 1/2 base times height. The base is 5 seconds. The height is 3 meters per second. Multiply those and divide by 2. And hey, you guys, just so you notice, we're going to do a little bit of cancelization here. All right, so look it over here, down here. The seconds and seconds, they're out of here. All right, they cancel. The meters per second, that second is in the denominators. And over here in the time, it's second in the numerator. So they cancel, and you're left with meters. And that's the answer. Now, that is the triangle area formula. If you look at the picture and interpret it correctly, you could figure out 1/2 base times height. Now, if you want to use the 1/2 AT squared, boils down to the same number. And we would call that the kinematics equation. That's a word that is in our textbook, kinematics. Basically, kinematics means the study of motion itself, excluding the forces. that may produce, we're going to start tackling forces today, but kinematics equations. So if you did get tripped up, there's your calculation. All right. Now, let me pause for questions on this or the previous question. Yes? It's the same A from the previous problem. And so, yeah, so you know what? You should make a practice of jotting down the question, and if there is a diagram, try to jot that down. And I did reuse the same diagram, so it's delta V is positive 3.0 meters per second, and numerator delta T is 5 seconds, so 3 over 5 is 0.6, and that's why you have the 0.60 meters per second over here, okay, in the second formula. Another question over here? Was that? All right. Was that a good answer for you? All right. All right. Let's do a kind of a smorgasbord velocity graph. Go ahead and sketch this graph out, and I'm going to give you a question. Better sketch this one out. What's your name again?
Brandon?
No, the young lady that asked the question. Sarah. Sarah. And Brandon. And everybody else. Better graph this in or sketch this into your notes, because I'm going to ask you a calculation about this. This kind of a combo graph, a little bit of acceleration, a little bit of constant velocity. All right. The first interval is a regular acceleration, so you're going to use a distance triangle. Here it is. I shaded it in, kind of cross-hatching here. And then the second interval, from 1 second out to 2 seconds, is just regular constant velocity. So I use the distance rectangle there. And then the third interval from 2.0 seconds to 4.0 second, it uses a distance triangle on top of a distance rectangle. So there they are. Here's the distance. All right. So whenever you have something that's not smooth acceleration, not constant velocity, you might not have a triangle, but you can always break it down maybe into small triangles, kind of pixelated up, as I did in chapter 1 with some of the diagrams leading up to the velocity triangle. But anyways, any motion, any velocity graph, you can always kind of divide it up into subrectangles and subtriangles. Question here in the front.
Number 2 should say distance rectangle, right?
Second interval. Oh, you're right. Ooh, Dr. B. Okay, thank you. Typo. Second time interval is at constant velocity. So use a distance rectangle. That should read. And it's this one here, cross-hatched from lower left to upper right. Now, right next to it is a bigger distance rectangle, and I did get that one noted correctly in number 3. That one's cross-hatched from upper left to lower right. And then the second distance triangle up here has got cross-hatching. Now, here's a question that I want you to work on, and we're going to sketch this. So sketch this diagram and label it carefully so that you know all the sizes of all the rectangles and triangles and stuff, because I want you to calculate the total distance traveled. Now you can do that from this sketch, all right? And we've done a couple examples of triangles, a couple examples of rectangles. Now let's put it all together. So sketch this, and this is going to be the calculation for the next iClicker question. And what I want you to do now, and so I'll just take this over here now. Here's your diagram. And on this one, what I want you to do is hit the refresh key. There's a blue refresh key on your calculator. And when you get that, you'll be able to start typing in numbers. Now the numbers, what does it come up to? Does it come up with 0 or 9? 9? 1? Okay. You use the up and down arrow key to type in a 1 or a 7 or whatever you want. And then below that or above that is the decimal point. Okay, so I want something point something. 1 decimal point. And hey, you guys, I'm going to turn the lights on because the decimal point is really tough to see. It's really tiny. By the way, you know what? I think maybe some of you guys on the, I think a foible in Web Courses Canvas, you may have been getting incorrect answers or getting graded incorrect for some of your times or distances if it was a number between 0 and 1. I think in Web Courses you have to type 0 point something. You can't start with a period. You can't start with the decimal point. And I think maybe that was blazing up some of your guys' homework. Same thing here on this one. If you get 0 point something, type in 0 and then the decimal point, and it's really small. All right, so go ahead and take a minute or so and just, and we're going to go over the calculations. So and if you have a neighbor to talk to, talk. And if you don't have a friend sitting next to you, make a friend. And if you don't have anybody sitting next to you, come up here and sit next to Miss Darian. And hey, you guys, you may have something like this on your next exam. And your next exam is your first exam is next Thursday. It's coming fast. We're going to be in December in about 5 minutes. It's going to seem like in about 5 minutes. We're going to be going outside. Right now, you go outside, you're going to sweat. It's going to seem like 5 minutes. We're going to go outside and freezing our off. Darian, can you walk around and... The large triangle? There's 2 triangles. I see you guys working hard. Erica, how you doing over there? See, this is the kind of thing that you would call, those of you that are ed majors, this is a synthesis question where you're putting together 2 things that you've previously tackled separately. Or as they say in the big leagues, we're putting it all together. Boy, this is interesting. Yeah, do you have ready? There, see if these guys are doing their clickers correctly. Yeah, and when you put in your number, make sure you hit the send button. And hey, you guys, you can change your answer if you want. Just type it in again and hit the send button. Are they doing it correctly? All right,
Are we
good.
using the same acceleration value for this question?
No, you're using this data here. Use this. That's why I said sketch it carefully with the numbers, and you can make all your sub-calculations from the diagram if you... You know, everything's up there for you to calculate a couple accelerations if you want. 1 minute. Hey, Brandon, did you get it clicked in?
Yeah, I got it.
20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys got. All right, here's the distribution. Let me go to the presentation mode. Here's the distribution of answers. A lot of you voted for 5.5. Some of you were down in the levels below that. Let me see. Some people have 6. 14. Wow, 27.5. I have 5.25. Wow, there's a bunch of fractions in here. I'm looking for 50. Here's somebody with 55. One person has 55. You know what you did? You didn't do your decimal point. Now, if this were the midterm and I was looking at the spreadsheet, see, the software records all your answers in a little spreadsheet, and I can go and look at it on an exam. I would see that person with 55, and I'd say to myself, okay, I'll give them partial credit because they messed up the pesky little decimal point on the display, which is a pain in the neck. Anyway, here's the solution. All right, first time interval, 1/2 base times height. The height is 1, the base is 1. That area is 0.5 meters. Second time interval. The height is 1, the base is 1, and it's a rectangle. So this one adds another 1 meter of travel. The third interval. Now this is the one where you have a combo. So you got to hit the distance rectangle and the distance triangle. Okay, the rectangle is 2 by 2. No, excuse me, 2 by 1. Okay, 2 seconds across for the base and 1 meter per second for the height. The way that I've got it sketched. And then the distance triangle is 2 units across for the base, 2 units high. So 1/2 base times height for this one is also 2.0 meters. All right, and a bunch of you got that. The total answer is 5.5 meters. And just a side note, this finishes up the total blaze that we've made of chapter 1. And we're going to push through the short chapter 2 about Galileo's discoveries concerning motion. But let me pause for a second just to see if you have a question. Yes.
How'd you get the distance for the second rectangle?
Distance for the second rectangle. How did I get it? Base times height. The base is 1 second. The height is 1 meter per second. Well, V delta T. I'm doing all this mentally. I mean, you could do this all mentally if you have a good sketch. Just, base times height, or 1/2 base times height if it's a rectangle, triangle. Yeah. Another question. Yes. Well, that's what this list is. The list is, and I'm basically all I'm doing. It's mental arithmetic here. I'm doing base times height for the distance rectangles. I'm just going by the graph. I'm not using the formulas. So I'm just doing base times height for rectangles, of which I have 2. And then 1/2 base times height for each triangle, and I've got 2 of those. So item 3 here, the third interval, I have a distance rectangle. That's this guy here with crosshatched. And then I have a distance triangle. That's this guy here with this one, with this hatching. All right, so for this one up here, 1/2 base times height. And if you look at the sketch, if your sketch is labeled carefully, you can figure out the height of that triangle, etc. Does that help? All right. Another question. All right. Let's talk about the idea of driving a Ferrari off a cliff, which is something I believe I mentioned in the textbook in chapter 2. And here's a figure from page 29, which is the path of a Ferrari that somebody drives off a cliff. And they do it in movies and stuff. I don't know if real life people have ever done a Ferrari off a cliff, but now what's important for us is this fundamental argument that Galileo battled with about 400 years ago, about the time of Shakespeare. So when Shakespeare was over there writing Forsooth and all that stuff, Galileo was thinking about driving Ferraris off a cliff. And it's interesting, he was in a battle with, not really with Aristotle, but with the people of his day who followed Aristotle. And Galileo himself liked Aristotle and studied Aristotle, as most philosophers did in his day. Aristotle was still influential, more influential then than he is today. He's pretty influential today, but he was even more influential then. But Galileo thought that he did not quite get the full idea of motion correct, and it led to a lot of problems and arguments between Galileo and a lot of the university faculty of his, around Italy and around Europe in his day that followed Aristotle. So in Aristotle's view, motion requires a mover. And all motion is from a force of some kind. And both Aristotle and Galileo agreed, there is a state of rest. Okay, obviously. Sitting on your eating donuts, you're in a state of rest. But if something is in motion, Aristotle said if it's in motion, it's got to be because something is pushing it or pulling it, some kind of a force. Now, Galileo said, yes, there are forced motions, but also there are unforced motions which do not accelerate. In other words, they neither slow down nor speed up. And that is the state of motion that Aristotle would never have admitted to. Aristotle would have said, Galileo, take a hike. You're out of here. He would have given Galileo an F in red ink on his essay. So if you have ever got an F, or now I know everybody in here is a genius for writing essays and stuff because they're really a lot of fun and everybody enjoys writing essays. Yeah, right. Anyways, if you've ever gotten an F, Galileo might have gotten one too if Aristotle had been his grader and if he had said something like this, that there are unforced motions which don't accelerate, they don't speed up, they don't slow down. And for him, he thought of it, not in terms of a Ferrari, but he thought of it as something traveling along a horizontal plane and then suddenly dropping over the edge of the plane. In other words, kind of like driving a Ferrari off a cliff. So here's this hypothetically frictionless horizontal plane. Let's get down to the brass tacks here. He said, all right, get an object up on this, up above the surface of the earth on a frictionless horizontal plane. And on that frictionless horizontal plane, it is indifferent. And underline the word indifferent. That is exactly the word that Galileo used. He said it's indifferent to either being at rest or in motion. And that would have driven Aristotle wild. And it did drive the Aristotle disciples of Galileo's day wild. He said, if it is in motion, it will persist at constant velocity until it leaves the plane. So up on that flat horizontal, like a super smooth skating rink, it will stay in motion at constant velocity. So same speed, same direction until it leaves the plane. In other words, until the Ferrari drives off the edge of the cliff. So something like this. Did you ever see this movie where they drive this thing at the...
Mission Impossible?
No, it's Fast and Furious. They do it in a bunch of movies. It's pretty cool. I don't know how they do it, but they've been doing it since the 80s, I guess. So Galileo proved that this indifferent state must exist, and he used ramps to prove it. And so we'll start the proof here on this page. So here's the premise. According to you and Aristotle, this is from page 27 in the TEXT BOOK. The object will move along the horizontal plane only if it experiences a certain amount of push force. Okay, so that's the thing that Aristotle would have said. All right, yeah, you can move along that plane, but if there's no force on it, it won't be moving. It's got to have a force, something pushing it or something pulling it. All right? And he wrote a lot about, you should see his description of an arrow. An arrow that flies through the air, the air goes from the front of the arrow to behind the arrow and then pushes the arrow further forward. It's really complicated what Aristotle wrote about. And one thing Galileo did was simplify it. Anyway, so starting with this premise that motion at constant speed requires a certain amount of push force. So here's an object. And here's what Aristotle says. You need a bit of push force here. Constant speed. All right, here's V equals constant. And Aristotle said, yeah, okay, you can have that, but it's going to require some force. some kind of a force, you know. And Aristotle said, well, yeah, if it's small enough, it might require about 0.02 metric units of force, right? So that's kind of our generic force unit, the metric unit of force. All right, and so that's Aristotle's view. There's always, if something's moving, there's always something that's moving it, pushing it or pulling it from point A to point B. And so let's label that as this little teeny vector P. P for push force. And this is actually the same notation that I use in the e-textbook around page 27 in that area. All right, now let's see what Galileo would say. Because Galileo said, Aristotle, you're out of here. The student has become the master, and I can prove it, Aristotle. So let's look at Galileo's counter-argument. Okay, so here's the car, and Galileo said, all right, one of the things that this car's got is some weight force. Okay, you know, it takes some. You know, if you're carrying it from point A to point B, it requires some muscle power to lift. Well, you couldn't really lift a car, but I mean, a toy car would require a little bit of push, force to lift it. So it's got some weight force, and it's going straight down. And Galileo would say, all right, very nice conjecture, Professor Aristotle. This car also has a bit of weight force, and so let's say that this one's got about 0.1, a little bit more weight force than the push force that you're talking about, Professor Aristotle. So Galileo might say, all right, well, let's give it a good round number, 0.100 metric units of weight force. Okay, so write a vector downward, make it, eyeball it in as 5 times longer. Mine actually is 5 times longer than Aristotle's push force. Okay, and the push force is perpendicular here along the plane, and the weight force is straight downward. Okay, now let's copy those vectors. Now watch what I'm going to do, and then then when I'm done, you can make a copy of the diagram. So I'm going to copy the P vector. See, there it is. There's the copy of P. Here's the copy of W. And what I'm going to do is rearrange them. Here comes P. And let me tilt it over here so it's pointing downward now. All right. And let me take the weight force and slant it at this slant level so that the top of, or the tail of the weight force is at the tail of the push force. And the tip of the weight force is at the same level as the tip of the push force. And if you do that, you have a right triangle. And that's the right triangle I want you to make. And Galileo said, I can make a ramp for which these are the proportions. The height of the ramp and the hypotenuse of the ramp are a ratio 1 to 5. Okay? Aristotle said 0.02. Galileo said 0.10. That's a ratio of 1 to 5. And Galileo said, to defeat your conjecture, Professor Aristotle, let me build this ramp. Now, why is this ramp important? Because Galileo knew that the amount of force that gravity provides, if the car is on this ramp, the force down the ramp that it gets, it doesn't get the full gravitational force because it's on the ramp, so it doesn't accelerate at 9.8 meters per second squared down the ramp. But it still gets a little bit of acceleration down the ramp, and it's from this force, just a little. And these two arrows here And this triangle, let me back up. Here they are. Let's redraw them. There's the push force. Here's the weight force. Make your right triangle. And then take your two arrows and rotate them like that. And this weight, this little component up here is equal to the amount of weight force going down the ramp. And so what that means is, Aristotle, you are out of here. You are overestimating. Because 0.02 metric units of force is what you need for this ramp. It's more than what you need for a flat plane. This ramp is the force on this ramp. This is the force, and this is the shape of rank for which 0.02 units of force produces acceleration. So on the flat, you don't need it up here. So go ahead and put a big X through here. You don't need that many metric units on the horizontal plane. You need it over here. You get it over here from the weight force. Here's another way to say it. A flat plane will require less than the inclined plane. So whatever else you say, the flat plane requires less than 0.02 metric units. All right? And so as long as you have something on the plane that has a weight, and as long as Aristotle says, a certain amount of push, you can make a triangle and say, nope, whatever push force you're proposing, that's the push force, or that's the gravitational force down the ramp that you get from a ramp, not from an inclined plane. And for that reason, no matter how small you make your original push force, Professor Galileo, either 0.002 or 0.0002 or anything smaller, Professor, and this is a quote from page, I believe, 28, Professor Galileo or his deputy, oh, that's us. We're his deputies in the present day. We can always build a ramp to contradict you, Professor Aristotle, and therefore, you are busted. So, in other words, the proof is complete. He proved that Aristotle's idea that there has to be a push force even on a frictionless horizontal plane is wrong. And that therefore, on a frictionless horizontal plane, an object is indifferent to the state of motion. Yeah, it can be at rest or it can be at a constant velocity. Same speed, same direction. It doesn't matter. It doesn't need a force for that. Okay? And that is what we sometimes call the inertial state or inertial motion. The whole idea of inertia. I-N-E-R-T-I-A. In other words, an object with no forces acting on it will stay in a state of motion at kind of like this little hound dog. Constant speed and constant direction as long as you're on that plane. And hey, you guys, that became the very first law of Sir Isaac Newton. Sir Isaac Newton's 3 laws of motion, and now we're starting chapter 3. We kind of breeze through chapter 2, and you can read more about chapter 2 and dig into it. We just it's pretty short, and we just blaze through the main part of it. It's figuring out how ramps defeat Aristotle's contention. But yeah, this idea of motion at constant speed, constant direction, it was actually a revolutionary breakthrough and at the time very controversial. But Galileo used it to figure out the trajectory of ballistic projectiles like cannonballs. And we will talk about that on Thursday, and we'll go into some more about Sir Isaac Newton's laws of motion. But let's do, there's a picture of good Sir Isaac. And here's the way he wrote it. Every object retains a state of rest, or, to warm the heart of Galileo, its state of uniform straight line motion, unless acted upon by an unbalanced force. Now, if you're in the Ferrari and you're coasting along at 50 miles an hour, you're happy as a clam until you get to the end of the plane. And then an unbalanced force kicks in, gravity downwards. All right? And that's when you got to bail out, you get hit your parachute or whatever, or put on the flux capacitor or something like that. Anyways, so an example is an apple in an apple tree. And the famous, this is another famous legend. Sir Isaac Newton, he discovered the law of gravity after an apple fell out of an apple tree right onto his coconut, right onto his noggin. Now, nobody knows if that's the case, but supposedly it's true. And some people can even point to the apple tree or to descendants of that apple tree that provided the apple. All right, so an apple in an apple tree has a pair of balanced forces. The stem attached to the branch pulls upward, right? So your apple has some weight force pulling downward, all right? So the stem is, put a little bit of, just enough to keep it on the branch, And then, eventually the stem weakens because it dries out in the autumn, and the balance fails and down it goes. Okay, so that's kind of an easy case of it stays at rest because there's no unbalanced force. Now, in the case of Galileo, on that mythical frictionless plane, you can't make a mythical frictionless plane out of jello because it doesn't have any upward rigidity force to support a Ferrari or anything else. Okay, so it has to be, so his hypothetical frictionless plane had some upward force of rigidity from the plane itself, and then of course the downward force of gravity on the Ferrari. And similar thing here. Now here's some pictures. And actually, this is not figure 219. It's figure 219 in the old textbook. But it's a little discussion about what happens to you when you ride in a bus. Now, in the textbook, there's a discussion about riding in the bus. And basically, when the bus is moving at constant speed and you're standing in the aisle, you can just, you don't have to brace yourself or anything, all right? But as soon as the bus starts to turn right, as in this lower part of the diagram, then you want to keep going straight because you're not buckled down to the bus. You're not bolted in. Right now, the seats are bolted in. The roof is bolted in. Everything else is bolted in except for you. All right, and if you're sitting in a seat, you're kind of semi-bolted in. You're fairly stable. But if you're in the aisle and you're not holding on to anything, you're going to keep going straight for a second anyways. The bus is going to go off to the right, and so you're going to bump your left hip into the seat next to you. All right? And that's what this picture shows. All right? So there's a force that changes the state of motion of the bus, but not you. All right? The only thing that does go to the right is your feet because they're attached to the floor of the bus. And if the floor of the bus were made of ice, a frictionless ice skating rink, and you were wearing Teflon coated shoes, even that you just keep. That'd be kind of cool to see what would happen. You know what would happen? You know you just go. You'd slide right to the left, your whole body. Anyways, the bus moves forward. If the bus moves forward, you're going to lurch backwards. Right? So you're standing in the bus, and they speed up. Straight ahead, but they speed up. You're going to be still in the same state of motion as before. So if the bus is going at 20, and then at a constant speed, and then speeds up to 25, you're still going to be going 20. So you're going to tip backwards at 20 miles an hour relative to the bus going 25. Until your neighbor in the back, she says, whoa, buddy, easy does it, and catches you. Because you don't want to fall down and break your head open. And then here's the concept of turning right and bumping your left hip. Question?
Anytime a direction of change occurs, you're always going to be moving in the opposite direction.
Yeah, well, it seems like it's the opposite. You're actually going in the same direction as you were, but because everything else is going in to the right, it looks like you're going to the left relative to them. So it's one of those 6 of one, half dozen of another, depending, so everybody if you're in the bus, yeah, it looks like everybody suddenly goes left. I mean, because like the security camera in the bus, it's fixed. It's looking down, and So if they have a sudden turn to the right, it's gonna. You don't really notice it unless you see people, blazing off to the left. So anyway, so that's why you have to stabilize. That's why I have all those little handholds that you can stabilize yourself. And they're necessary unless your bus never changes its state of motion. But if that's the case, then you ain't getting off. Either that or you ain't going anywhere. So, and notice that these are separate interactions. The whole forward and back, left and right, you can have a little bit of both. You can be turning right and speeding up. And actually, that is the case. If you're getting onto the interstate, you're turning, let's see. You're turning gracefully to the right, a slow turn to the right as you speed up to get on the interstate. And as you slow down and turn gracefully off to the right. So that would be a case of both happening at the same time. They are separate. Now here's another one. Forward and back, left and right, for the bus as well as for this football player catching for the football going through the air. And so you analyze the motion of the football in terms of vertical and forward and back motion, just as you could stabilize yourself in the bus either starboard and port or forward and aft. Okay, and the same thing with this football going through the air. So that's a little bit about the first law of motion. Let's talk about the second law of motion. The second law of motion is something that Galileo didn't come up with. Newton came up with this one. So this one was invented by Newton. And it has worked out very, very nicely. It's very well verified. Second law of motion. If you do have unbalanced forces, you are going to accelerate. So if you do drive off the edge of the cliff, there's no cliff to support you anymore. The only thing that's acting now is gravity, and so you start curving downward. All right. So what you do is you try to figure out all the forces acting on you and add them up. And if anything does not balance, then you call that the net force. And the notation for that is a subscript with the word net. And it can be used as a vector or just as a what we call a scalar, S-C-A-L-A-R, without a little arrow over the top of it. So, for instance, Dwight Howard versus LeBron James. If Dwight Howard has 100 metric units of force to the right, and LeBron James has 80 units of force to the left. So let's denote that leftward force as a negative 80. All right? You add those two up. So 80 plus a negative, 100 plus a negative 80 is positive 20. So the net force is 20 metric units of force to the right. All right? And that's an example of how you figure out the net force. Now, Sir Isaac Newton says, all right, look at the net force, and if the net force is not zero, you're going to have acceleration. All right? And he said the more net force, the more push you have from your net force or pull, the more acceleration you have. Also, the more kilograms of mass that you have, the less acceleration. So if you have so item 2 here, more push, more acceleration. If you have a little shrimpy first grader trying to push a grocery cart that's loaded, he's going to be able to push it, but he won't be able to get it going very fast. Versus us grown-ups pushing a loaded grocery cart, we're stronger, you know, we're grown up, and we're going to be able to push it a lot more with a lot more acceleration. Now, take you with 2 grocery carts, one of them loaded. Let's see, what do you get at the grocery store that's really heavy? Olive oil, any kind of liquid. You know, like 10 jugs of water, 10 jugs of milk, 10 things of olive oil, a bunch of canned Spam, you know, like a lifetime supply of Spam, and all of it in your cart. And then half of that in the other cart. Still a lot. But so the really heavy cart, if it's you pushing the same amount of push force, it's going to be harder to get that loaded cart going versus the one that's halfway loaded up. All right? So that's what this means, number 3. Now, the formula that we have to measure to get the acceleration is basically this. That the acceleration is equal to the net force divided by the mass. All right? And so the numerator is the push or pull from the net force. Now, if that's 0, you don't get any acceleration. All right? So that's LeBron James and Dwight Howard with equal pulls to the left and to the right. You know, they battle it out, no acceleration. But as soon as that becomes either a negative number to the left or a positive number to the right, you're going to get some acceleration. Now, the other thing is, the mass of an object is never going to be 0. It may be really small, but it's never going to be 0. The only thing in the universe we think that has 0 mass is light. Photons of light appear to be massless. And they have a whole different kind of physics that governs them. But for objects that have mass, that's in the denominator. And so the more you have in the denominator, the smaller your acceleration. Now, another way to write this is F net equals ma. And that particular student, or excuse me, that particular equation is like if you ever have a friend or a roommate that's an engineering student and they've got this equation F equals ma, they've got it on the brain. I mean, it's just like drummed into them, and they just, if you could dissect their brain, you'd see a big area that's completely taken over by the concept of F equals ma. So if you ever want to trick an engineering major, while they're doing their, and engineering majors, they can be kind of annoying, they know everything and whatnot. So if you ever want to get the goods on them, while they're doing their homework and they're pretending that they're really smart and everything, just go up to them and say, oh yeah, F equals ma. You will be right. And the engineering major will think, how the heck did they figure out that? Just by looking at my homework. Because I guarantee you, it will always be true. All right, let's dismiss. Homework 3 will be activated by 2 p.m. You're dismissed. I'll see you on Thursday.